Between now and lunch, we have 4 user presentations from TI, Microchip, ST, and Benu Networks. Our first speaker between now and lunch is from Texas Instruments, Vishal Goel, who's a senior lead engineer at TI. Vishal leads the virtual platform development team in Texas Instruments. He has led and worked on SystemC-based virtual platforms for several multi-core SoCs in TI, focused on video, apps and processors and infotainment for the past 10 years. Okay. And the title of his presentation is Hybrid Simulation and SystemC HDL Co Simulation. Thank you.
Thank you. Hi, my name is Vishal. As per my introduction, I'm from the SystemC background. So I'm able here because I'm not so much into the verification and validation. So we got this opportunity because we have seen solutions from different vendors where we tried this hardware and SystemC co-simulation. So internally we were driven by a need to have a lower cost solutions, and that got us into experiments. With the help of TVS, we managed to do something, and TVS invited us to share our experience with you guys. So thank you, TVS, and thank you for joining this presentation. So in this, I'm going to set up the context for the need for hybrid simulation as seen by Texas Instruments, and followed by this will be the case study that the proof of concept that we have done. Sorry about the bad graphics. I could not get any hybrid element. I know it's a transformation, not hybrid. So the presentation is based on the work done by my colleagues Asif, Amit, and myself. So we had support from one of our interns, Vignesh, and we had Pratish. He's actually DV and RTL expert, and we had support from TVS, Mr. Bharat. So, God. That's not so great. So before going to the presentation, I would like to talk about the different phases of the pre-silicon software development. And I think this is the most important message. This was the reason we started this activity. We had discussions with our design teams. We have several teams like AVV, application verification validation teams, and SOC level design verification teams, validation teams. We were always supporting them on 4 different flavors. One was architecture-based simulators, architecture evaluation platforms, software simulators, that is SystemC-based simulators. And then as TI, we offer RTL simulators, and we have FPGA-based solution from different vendors. I will not talk about architecture platforms. So the scope of this discussion would cover all the platforms which were used for software. That will be SystemC, RTL, as well as FPGAs. So so this is standard stuff that SystemC kind of simulators allow you to do. Well before even compile 0 of RTL or chip is available, the software development can start. And by the time we have some stable RTL, some other teams can jump on board and start using that simulator. And by the time the RTL is frozen, let's say the FPGA is available, some other teams come up and the final software validation starts happening including the performance measurement, performance validation, and verification starts happening on those boards. So we have been doing this for a couple of decades, actually, about pulling the software development aspect by 2 or 3 phases. That is, software development can start right after the definition of the chip is in place, and we have a lot of PCs already available. The fact that a lot of IPs are reused, we are able to put up the pre-silicon simulators very early, and the software development starts almost as early as compile 0. However, the other 2 phases is where we were struggling, and after a lot of input from the teams inside TI, we decided that we have to work on hybrid simulators to star condition about a low cost to enable the DV, AVV, ROM development, etc. To provide them in a platform which can be used to at least start writing software which will work on the IP level DV as well as well, to some extent. And finally, the same software which can start getting developed earlier, and by the time we have subsequent compiles, the same software can be used and can get matured and can be used early. So, so this is the primary reason. This is a macro level diagram, macro level explanation why we wanted to do, or we want to do, or we have invested in hybrid simulation. So now I'm going to micro level details about why we care about hybrid simulation. I think this is not a news to anyone. The complexity of SOC is increasing, and creating test benches around individual IP with respect to a new SOC is becoming a big challenge. The IPs are reused across different SOCs. That is again become a norm. The problem with that is that SOCs used in one, or test bench is used in one IP SOC flavor cannot be used in the same IP but different SOC context. And it obviously it puts a limitation on the reuse of the validation code that we have across the various chip programs. And if we have the entire test bench in RTL, it of course puts a limitation on the speed, the kind of testing we can do, the kind of regressions we can do, the kind of how much testing we can do to qualify the entire RTL for, let's say, for freeze purpose. And there are challenges of starting early because the RTL itself may not be stable, the software itself may not be, it will also have bugs. And to identify where the real problem lies, we may have to go back and forth. So we need for not only co-simulation but co-debugging. At the same time, for the IPs which are not changed, and let's say, so 80% of your SOCs are reused, and the new 20% IPs are, let's say, in RTL form now, thanks to the solution. For the 80% which is being reused, we don't have to limit ourselves to the limitations of RTL environment. We can very well move to advanced debugging features that system like software simulators, aka SystemC simulators can provide. So we see that, again, another microscopic view of the why we want to do hybrid simulation. We think this hybrid simulation can help us, or a co-simulation can help us with improving IP design validation at a SOC level. It can help us improve the quality of software in the pre-silicon stage. And overall, we foresee that it can help us improve some aspects of the overall flow of the chip design. So with respect to IP design verification, so one thing, as I mentioned earlier, the IPs are being reused in different SOCs, and writing VHDL Verilog-based test cases at IP level is okay, but when we start writing the same test case at SOC level, it may not always be easy. In fact, we have seen that the number of test cases written gradually decrease as we go from one IP to subsystem to system, because maintaining the same complexity in the IP things like Verilog may not be easy. I think Vijay did mention that we should write those test cases in such a flavor that it can be reused, think of APIs, etc. But we are hoping that with this kind of approach, we can write the software in the test cases in the C flavor. That makes it easy to maintain, write, and reuse across platforms. So because the same software can be reused, where partly it is running on the SystemC and partly it is running on the RTL, the same software can be reused across different phases. For example, as I mentioned earlier, at SOC level verification or application level, the final chip level verification. So this helps us improve the software becomes increasingly better as we go along. So what we foresee is that, in fact, we have seen it already, that the low-level drivers become nearly production quality by the time the final silicon is actually available. So this is from the IP design perspective at SOC level. We see, so me being pre-silicon person, I always focus more on what pre-silicon software guys can benefit from. But this is more about, not about development of the software on pre-silicon, but it's about because development platform will still remain SystemC, etc. But this kind of a platform can help us improve the quality of the software, because the software is being run on a more accurate platform, be it in terms of functionality or be it in terms of accuracy. Accuracy in the sense, sometimes we may not have, so I've jumped to the second bullet here, by the way. So where here, sometimes the SOC may not have IPs available in the C, may be reused from the previous SOC, but C model may not be available and maybe under development, or it may happen that, let's say we bought some IP from a third party and we get only RTL. We may not have luxury or enough information to create the C models. In such cases, such an approach can help by completing the SoC platform early by plugging in the RTL. So in rare case, if during the pre-silicon stage, if someone wants to use test the software in the timing accurate fashion, RTL could be better investment than trying to write the cycle accurate model flavors of the IP models. From the overall flow perspective also, we see there can be improvement. That is, so when it comes to writing a test bench around an IP from the design validation perspective, so one option is to keep on creating as much as possible in the test bench or system around the IP. The other option that we think, thanks to co-simulation, will be to use SystemC to complement the rest of the system. So the entire the software development can happen as if it is happening on the final chip. So it helps reduce the time spent on creating the test benches for RTL. If we continue on this approach, the RTL fixes can be provided early to software guys rather than going through the SoC guys. Let's say they may have to do a respin of RTL, or in the subsequent stages, the let's say Zego, etc. So of course, if the good part of the environment is going to be SystemC and only the core new IPs are going to be in RTL, the simulations are going to run faster. Not 100% accurate, but much faster than the pure RTL only environment. And finally, because we are doing not only core simulation, we also have managed to enable core debugging. We can debug the RTL as well as software as well as the SystemC IPs all at the same time. That makes it easier to debug. As I said, because it may happen that RTL itself may have bugs in the initial stages. And the fact that simulations are running faster, we may be able to run larger or more frequent cycles of regressions. So these are the things we think we want to target, and we understand that we cannot achieve every. We are not going to replace IP DV. It is more about writing the test cases at the SoC level, and we cannot replace the actual RTL environment writing the test cases in Verilog, HDL, etc. system where it's going to continue to happen. And we cannot do, so we think we cannot do performance evaluation using these platforms because as per our definition, the IP is going to be hybrid. Good part of it is going to be non-cycle accurate. In fact, more probably at the TL3, TL4 level from the SystemC terminology perspective. And finally, this approach may not always work for complex IPs, depending on complexity of the IP. Let's say it has multiple threads, and one request going into an IP comes out from the IP and again lands into SystemC environment, and there can be deadlocks. And that is one aspect. The other may be that the complexity of IP may dictate the speed, and it may become a bottleneck in the overall performance of the system. In which case, the benefits that we see with respect to speed will not be seen. So having explained, I hope I explained why we look forward to using co-simulation. And after going through that, we have looked at the multiple options that we had, two approaches with respect to co-simulation. One was direct signal interface, the other was direct programming interface, DSI and DPI. So we have tried multiple approaches, multiple solutions in DSI as well as in DPI. So in this case, we are going to talk about only one solution based on DSI. So the DSI will be about when the two paradigms connect at a pin level, whereas in the DPI mode of operation, the two paradigms, let's say RTL and SystemC, they allow making function call into each other. So so the work that we have done targeted this certain use case. We picked an IP called display subsystem, which was available as an RTL with OCP interfaces, and we wanted the co-simulation environment will have the rest of the stuff into SystemC. The primary master being Cortex M4, and it would all run under TI's Code Composer Studio debugger. So the solution that we targeted, as I mentioned, was going to be based on DSI. It will involve the bridging the gaps between the RTL running at a pin level, which is called TL0 in SystemC terminology, and the SystemC model itself, let's say Cortex M4, which is going to be running at TL4, blocking transport calls. So this would require us to write adapters from receiving generic TL4 commands and translate those into OCP TL0 and vice versa. And it may happen that the SystemC engine or the debugger may be running on one machine. In our case, our users prefer to use this entire thing to be running on Windows environment, whereas the RTL simulation may be running on a different machine or a different OS. In our case, it happens to be on Linux. So we needed an IPC mechanism, and we used a TCP/IP to make the connection between the two. The environment used so we had a third-party EDA tools for RTL simulation, and we used SystemC-based Cortex M4, and it was all running under TA's Code Composer Studio. So the approach used is demonstrated in an OCP kind of environment. So this is how the solution looks like for us. So now we have a SystemC environment where we have the Cortex M4, let's say one interconnect, bunch of IPs, DDR, and one of the IPs was supposed to be DSS, display subsystem. So this is all running under TA debugger on Windows, and the DSS IP is replaced by a proxy of a DSS, which receives a command as they are received from Cortex M4, and it transfers those to the SystemC environment using TCP/IP. In the RTL environment, the commands are received by a C thread, which is listening to the TCP socket, TCP port, receives a command, and using TL4 to generic TL4 to OCP TL0 adapters, it does a forward translation. And if the DUT or the IP has to do any transactions as a master, then the reverse path will be taken where TL0 to TL4 will be done, and the reverse path will be taken. Most of the time, the reverse path would land into DDR. So that I have not shown here. So speaking about adapters, so we reused a couple of adapters which were available from OCP community as part of the OCP TLM toolkit. They have provided adapters for TL3 to TL1 and TL1 to TL0. So we essentially just bridged the gap by encapsulating those between one adapter, which would take the generic TL4 commands, convert it into OCP TL3, and then use the adapters. And finally, the request translates into TL0. The adapters would receive the clock from RTL environment, and the adapters, because OCP is a very configurable protocol, the adapters needed to provide a lot of configuration APIs to allow the software, the system integrator to match the OCP parameters at system level. So this is how the data flow looks like. On the top, we have the TLM to slave port, which is gonna generate blocking TL4 commands, and we attach OCP extensions as configured at the bring up time, and then this payload goes through TL3 to TL1, TL1 to TL0, and finally lands on the RTL boundary. So we have a similar path. If the request has to originate from the RTL, the request from a request will be translated from TL0 to TL4 in the similar fashion. So in terms of IPC, as I mentioned earlier, we need IPC because the SystemC simulator may be running on Windows and RTL may be running on Linux. So we implemented a basic proxy client in the TA debugger, which sits in the memory map of the system as if it's like an actual IP, but it just receives the commands, and any CPU read write, it just translates, converts those into TCP packet and sends it to the other side. Where the other side is RTL simulators. RTL simulators a TCP IP thread, which receives the commands and uses the adapters, TL4 to TL0, and sends them to the RTL. So this is a code snippet which shows how the EDA vendor that we have used has provided us a convenient way to define a TL0 adapter. And this is on the left side. It says, I don't know if you can read it by integer. It's a foreign element which is based on SystemC. On the right side, the connections binding of the signal is shown, which is quite straightforward, name-based port binding. So the test environment was, we wrote simple C test cases, which would configure DSS to do some image processing and do a DMA from, after the processing of the image, that do the reading the image from DDR, do some processing and push the image back on DDR. The test case was compiled using the ARM compilers, and we were running it on Cortex M4 under PICCS debugger. So this is what we could achieve. We were able to run the basic SOC level test cases involving DSS, and we were able to develop, as part of this activity, we were able to develop the adapters that I spoke about. And these adapters we think are quite flexible, and these are reusable for any other OCP-based IP. And in terms of simulation speed, we didn't actually measure the speed, but we could see that it was quite useful simulator in the sense the entire cycle it took the speed degradation was not noticeable. So the complexity of the transaction, so as the complexity of the IP increases, the speed maybe will definitely be impacted. But as far as this access was concerned, the speed was quite good. And just as a proof of concept, we were able to verify that we were able to attach, we were able to put breakpoints within the RTL simulation as well as SystemC simulation and software debugger being the CCS again. So with this platform, we believe we can achieve all the benefits that we were targeting from co-simulation. This is finally what we think the co-simulation can help us with. Our DB teams can benefit from the co-simulation because of early availability of the test benches, which can match the final targeted SOC. And because the software can be written in C, good part of the testing can be done in C, it can be reused across from simulators to hybrid simulation to the final silicon. And it can also help improve the quality of the software in the pre-silicon stages, because we'll be running software on actual RTL rather than the C models. And by virtue of that, of course, we can improve the quality by catching the spec bugs early. And in case the C model as well as RTL is available, it becomes easy to correlate the spec, the C model as well as the RTL. And debugging of the RTL versus software issues is faster. I think I've covered this earlier a couple of times because we are doing a joint co-simulation and co-debugging. And the two specialists from the SystemC as well as RTL world can sit together and we can have hands on their respective debug environment and do appropriate debugging. So limitations. So what we achieved was for a simple IP. It didn't have too many threads inside, not too many execution going on asynchronous to the rest of the system. But if we have complex IPs, we'll have to think about how to synchronize such activities. And as part of the further work, we need to. So we did this activity for TLM transactions, the bus operations, and clock, but we have yet to complete it with respect to the interrupts perspective. And OCP is one of the buses we use. We also want to try out the similar thing for the other protocols that we use within TI, for example, CBA. Thank you.
Thank you. Thank you, Vishal. Very interesting. Do you have any questions for Vishal? One question. What simulation speeds did you reach with the combined?
So as I said, we didn't mention the speed, but let's say our normal simulator speed is running at, let's say, 10 MIPS. Okay. So that is normal simulation speed. And with the DSS integration, with the RTL integration, my gut feel is it was not less than 9. So it was less than 10%. But this is just a gut feel because by eyeballing, we could not actually see any noticeable difference at all, actually.
Okay. And one of the issues I've seen in the past is when you do debug, the software team is used to seeing a software debug and the hardware team is used to seeing waveforms. So how did you do the joint debug of software and hardware?
So that's actually interesting because I removed one slide which I thought was too cumbersome to put because that's what it showed actually. So we would have the RTL simulator running where we could see the waveforms. At the same time, we'll have a CCS code, the software level debugger.
Okay.
So when the software guys get stuck at a point, we can always switch to RTL. So of course we need two different people with the two different skill set, but it was possible.
Okay, so you could actually see a software debugger and a waveform at the same time.
Yes.
Okay, it's interesting. Okay. Okay, no more questions. So thank you very much to Vishal. Thank you.
Thank you.